In this video, I'm going to work some examples involving the formulas involving the indices of refraction. Here is my first example. I want to know how fast does light travel in water and how fast does it travel in glass. Remember that the index of refraction of water is about 1.33. And for glass, it's 1.5. To do these calculations, I relate the speed of light in vacuum, c, to the index multiplied by the speed in the medium. I can rearrange that so the speed in the medium is the index of refraction multiplied, not the index of refraction, the speed in vacuum divided by the index. You might recall that the speed in vacuum is a fixed value. It's 3 times 10 to the 8th meters per second. For water then, I'm going to take 3 times 10 to the 8th meters per second and divide by 1.33. And that gives me an answer of 2.26 times 10 to the 8th meters per second. For glass, I take 3 times 10 to the 8th meters per second and I divide by 1.5, which results in 2 times 10 to the 8th meters per second for the speed in glass. Here's the next example. I have a light wave incident upon a surface between air and water at 30 degrees, and I want to know what is the refracted angle. So begin by drawing a picture. This side I'm going to let be air, this side I'm going to let be water. Index of air is 1, index of water is 1.33. And remember, all angles are measured relative to the normal. So there's my normal. My incident angle, contrary to what I drew here, is given to be 30 degrees. And my refracted angle is what I want to know. To do this calculation, I use Snell's law, n1 sine theta 1 equals n2 sine theta 2. It doesn't matter which side you call side 1 and which side you call side 2. I'm going to let side 1 be air. So index 1 is 1 times the sine of 30 degrees equals the index of water times the sine of the unknown angle. To solve this, I first need to get rid of the sine of 30. That has a value of 1/2. 1 times 1/2 is 0.5 equals 1.33 times the sine of my unknown angle. I can rearrange this so that the sine of the unknown angle equals 0.38. And then to pull the angle out, I have to use an inverse sign. So theta 2 equals 22.1 degrees. And that is my answer. As expected, when I go from low index to high index, I refract towards the normal. Therefore, my refracted angle is less than my incident angle. For the last example, it's similar to the previous one. We again have an interface. We're told one side is air, the other side is unknown. But we are told the angles. The incident angle is 25 degrees and the refracted angle is 16.4. So automatically I should expect the index of my new medium to be bigger than air because I've refracted towards the normal. As with the last example, I use Snell's law, n1 sine theta 1 equals n2 sine theta 2. Index of air is 1. Multiply that by the sine of 25 degrees. Index 2 is what I don't know, so that's what I want to find. And I multiply that by the sine of 16.9 degrees. Therefore, n2 is the sine of 25 degrees divided by the sine of 16.9 degrees. And when you do that, You know, I've been saying 9. I've been drawing 9. The problem actually says 16.4. Let's make it 16.9, shall we? So now if I take the sine of 25 and divide by the sine of 16.9, I get out an answer of N2 equals 1.45, which is not exactly any of our materials, but this is really close to N being about 1.5, and remember that's glass. So most likely this material is some sort of glass.